Hey everybody, yes that's true, I am here. Thanks for your patience. Troy Carpenter coming to you live from the new Goldendale Observatory. Tonight we'll be talking about a certain thing that people always ask us about, so I kind of saved it till the end. Yes, the end, because next week will probably be our last show for a while, and there's a good reason for that. We're working actively on reopening the facility. I'm not going to give you any specific dates or times yet, but we're getting there, and that's going to take 10,000% of my bandwidth, and it already is. And the show is difficult to keep up in that context. We might reinitiate the show. We might restart it later once we figure out what our new operating schedule is going to look like and how the show can fit into our schedule. Yeah. So this is episode number 19, I believe, of Goldendale Observations. And so the next week, 20. I think 20 makes a nice round number. Yeah. And just so you know, to get you prepared right now, that show is going to be about all kinds of things, and it's going to be mostly question and answer. We're going to be going over space archetypes, different types of objects. Believe it or not, most of the different kinds of objects that exist in the universe, and you might think that's impossible, but if you're vague enough, you can cover a lot of ground pretty quickly. Okay, so tonight we're going to be talking about a triumph not only of astronomy but of computer science. We talked about computers a lot last week, and they've made new frontiers in astronomy available. Before these supercomputers became a tool of astronomy, we were limited to what math humans could do on their own. And of course, even if you have a lot of people, there's only so much math a given human being can compute. And as we discussed last week, human beings used to be computers and vice versa. But now with our extraordinary supercomputers that can do quadrillions of calculations per second in a networked manner, it's possible to answer huge questions with huge numbers associated with them. But it's not just that. Computers are not just thinking machines in the form of addition and subtraction, multiplication, division, and everything else. They are now considered thinking machines because in some ways they do think. The title of the show tonight was Imaging a Black Hole, and I noticed a few typos. People thought I meant imagining a black hole. They thought I had misspelled it. No. The word imaging is a verb. However, it's an amusing misunderstanding because, in a way, the famous image we're going to be talking about tonight is the product of a computer's imagination, because it is a image that is derived from not just information, data collected by telescopes, but also probabilities, guesstimations that are born of a computer mind's ability to very patiently consider all of the possibilities. Yeah. So we'll talk about that famous black hole picture. We're also going to talk about black holes a little bit on a 101 level for those of you who still don't know what they are, or those of you who tuned in just to find out what they are. I'm going to remind you, just like I do every week, please ask questions, especially tonight. Black holes and other high physics concepts are challenging, especially if you're uninitiated, so please ask questions and we'll try to answer them. We're not going to go too much into the weeds on astrophysics, but we'll answer what we need to. Don't expect me to perform any mathematical proofs tonight, but I'll talk about some of the math that's necessary to compute these various constructs, the things that we once thought were only imaginary on paper, then turned out to be real. It is amazing, by the way, that we're going to be talking about something tonight that was only predicted to exist about 100 years ago, and back then they thought, they probably don't exist. And now we know they exist, and now we have a picture of one. Yeah, so we're going to get to that. Okay, so let's see the chat. 2 computers, TV, full screen, nice Sony Bravia. That's good, Team Sony, like that. Testing latency. Okay, here we go. Clap. 1, I'm going through 3, 4, 5, 6. That's a long delay. 7, 8. Let me try a different thing. Yeah, hold that thought. To continue the always failed tradition, please ask questions now. We'll talk about something before we get down to the main topic. Clap. Okay, yeah. So that was. I picked the right browser to have the fastest. Oh, actually, that's really good now. So you know what just occurred to me? I can see myself. Let's see. High five to me. 2, 3. Oh, that's very fast. Okay, yeah. So, all right, latency is low tonight. We got 51 people watching. That's enough of you to generate questions and comments. So before I get down into the nitty-gritty of the topic, let's hear some questions, or maybe some hilarious comments. This red fluid I'm drinking is not blood. I'm not a vampire. This is fruit punch. Big fan of fruit punch. Good low lanes. Okay. Okay, once again, I have failed in getting you guys to ask me a question in the onset. So I'm going to just get right down to it. Chat moderation's in full force tonight. Feel free to ask questions. Someone will notice them and relay them to me if I miss them. What is a black hole? That's a good question. That's a very good question. Someone asked, does every galaxy have a black hole at its center? Apparently, yes. We're going to talk about that. True, black holes might not be a singularity. Also true. And by the way, that's directly related to the show tonight. Good. These are all good questions. Let's see. Excellent question. How can we image something where light cannot escape? Okay, I'm not going to answer all these questions right now, but they will be answered throughout the show. Kind of as a joke answer, I'm going to tell Jim, we can't take pictures of things that do not emit light. So we have to do things a little bit more indirectly, don't we? Now let me answer that using a topic we discussed a few weeks ago. We now have the ability, now as in recently, the ability to observe the presence of black holes and also neutron stars via gravity waves. So thanks to gravity waves, we no longer need an object to emit light, or if it does emit light, we don't need that light to actually reach us. Because one of the problems in space, and you're going to learn about this a little bit more tonight, it's not just whether or not something is dark or bright, it's whether or not you can actually see it, because there's not stuff in the way. Obstructions are a big part of the decision that gets made when it comes to observing things and how we try to observe them. So, just so you know, tonight is not about gravity waves, but I just wanted to point that out, that in a way it's less impossible now to observe black holes because they are the strongest gravity wave emitters when it comes to ordinary or typical objects in the cosmos. And now that we have the ability to measure gravity waves, we can detect black holes. Not surprisingly, because our techniques are limited and evolving, we're currently only successful in detecting some of the most extreme examples of black holes and also neutron stars. So the tiny ones, and we'll talk about size of black holes in a second, well, they're not always going to be detectable by gravity waves. In fact, they usually aren't. Okay, so I think it would be wise to start the show by answering the question, what is a black hole? First of all, let's talk about what they're not. Unfortunately for you, almost 100% of public discourse regarding black holes is driven by science fiction. And because that's where we tend to see them depicted the most often. Some of you might remember the Disney movie from the late 70s, The Black Hole. It's kind of a silly, ridiculous movie, although it's a classic. Many people like it. As I recall, that in that movie, they described the black hole as a sort of portal or gateway to other realms, other places. I don't specifically remember any quotes or dialogue from that movie, but I do believe the whole portal concept was in full force. I want to make something clear right now. Black holes are almost certainly not mystical gateways to someplace else, nor do white holes exist, most likely. Those of you who are not aware, a white hole is the concept of essentially the opposite of a black hole, where things falling into a black hole are spirited away to this white hole, which is like a nozzle spraying material out into some other universe. You know why that's probably not the case? You know why they probably don't do that? Because black holes exhibit different masses, and they seem to hang on to the mass they collect. Therefore, it is an object. It is not a hole. The term hole is misleading. It was coined for the purpose of describing its extremity, because it is like a hole in the fact that it cannot, as someone points out, emit light. But it's not actually a tear in space-time, at least not in a traditional sense, like a gateway or a door. It is a completely collapsed object, specifically a gravitationally completely collapsed object. So in other words, a black hole is something that's so heavy that it has collapsed completely. Because it can collapse no further. It has reached some limit of collapse, which could be, not necessarily, but could be a singularity, a point, which actually occupies zero volume and therefore comprises infinite density, which is, of course, mind-boggling and ridiculous. Black holes sound ridiculous. They were predicted by Einstein's relativity. Einstein himself and others of his time didn't like the idea. They thought it was a mathematical oddity that had to be worked out, that had to be solved, because there's no way such a thing could exist. And yet, relativity demanded that they exist. Simply put, the heavier something is, because of its mass and the concentration of that mass, the more it bends space-time. There should be a point where the object collapses and shrinks and collapses and shrinks and finally experiences runaway collapse, where it just keeps collapsing and shrinking and becoming more and more and more dense and heavier and collapsing better, etc., etc. So whether or not they existed was obviously a topic of debate for most of the 20th century. But we started to find evidence of things that had to be black holes because they were too extreme to be anything else. We're going to talk about that right about now. First, I'm looking at the chat, though. The closest black hole that we know of is I believe it was less than 2,000 light years away, which sounds kind of close. But there could be one next door to us. There could be one lurking next star system over. Probably not. But you don't need to worry too much, and that's actually part of the show tonight. One thing you should know about black holes, they are not the cosmic eating machines that they are often depicted to be in science fiction movies. Once a black hole has consumed the material within its sphere of influence, it will essentially stop feeding. By the way, that's an important topic tonight because we're going to be talking about the fact that we cannot see them. And if they're not feeding, that is especially true. If you want to observe the influence of a black hole, it's much easier to do if it's actually doing something, in this case, eating material. Yeah. Okay, so let's go over where they come from. Black holes are an example of dead stars. They are the completely collapsed cores of hypergiant stars. So I always have this image that I use literally constantly for my shows about the size of stars, and we discuss the fact that our sun is not a very big star. Oh, you know what? I have to get this set up. Hold that thought every night. So let me go back to my interface. Yeah, so here's this image that I always use of different stars. The little speck is the sun. Isn't that cute? These bigger stars are all famous. Betelgeuse and Antares are both examples of red supergiants. However, they will not become black holes upon their death. Their cores will collapse most likely into neutron stars, which are far, far less extreme than black holes. In fact, hypergiant stars are the only type that tend to naturally, and watch those words, naturally collapse into black holes. There are other ways that something can become a black hole, but as far as a natural life and death cycle, only the most massive of stars become black holes. And if you're wondering, if you want some numbers on that, one thing that surprises people is how even high mass stars are not that massive when you think about it. For example, a very high mass star, one that's considered to be extremely massive, supermassive, would perhaps have 60 solar masses. 60, so 60 suns is considered a high mass star or a supermassive star. Hypermassive stars are well over 100 solar masses. But even the most massive stars that have ever existed in the universe, and we've not observed these directly, we've only inferred their existence, in the very early universe may have been maybe 400 solar masses. So I want to give you some idea of how massive a massive star truly is. So we're not talking about objects that are millions of solar masses or billions, because such a star could not exist. If a star gathered enough mass to collapse into a black hole with millions of solar masses, it would never actually get to be a star because it would collapse immediately. It would be what we refer to as a direct collapse object. Now, that's an important topic because someone asked here about black holes at the center of galaxies. Stellar mass black holes are the ones that almost certainly came to be due to the death of a star. Stellar mass black holes are the ones that tend to have a few, maybe 5, 6, 10, 20 solar masses. Supermassive black holes, on the other hand, can have millions or even billions of solar masses. And they are almost certainly not the result of the death of a star. They are possibly primordial objects that came into being immediately after the Big Bang. And they turn out to be very important. It turns out, in this chicken and the egg conversation, the supermassive black hole might come before the galaxy forms around it, or maybe they form around the same time. Because in the early universe, you would have had extremely dense clumps of matter. And perhaps some of these clumps of matter, which could have weighed in the millions of solar masses, would have undergone direct gravitational collapse and become supermassive black holes before any of that material ever got to become a star. By the way, that is consistent with our observations of the cosmic background radiation. We have a universe that was clumpy. The aftermath of the Big Bang was not orderly, which is not surprising when you consider the aftermath of any given explosion. Explosions tend to be rather chaotic. And so where we had clumps or lumps of material, is a good chance that's why we had supermassive black holes form. Yes, so to answer the question right up front, the fact that supermassive black holes exist in the galaxy centers was big enough of a deal, but when we discovered that they apparently exist in all galaxy centers, or most of them, that was a huge deal in astrophysics. That was actually a revolutionary discovery, and that was a discovery that occurred in your lifetime. Everybody in this room, that occurred in your lifetime. The discovery that, much to our surprise, supermassive black holes reside at the centers of apparently all galaxies. They do vary, though. Just like everything else in the universe, not all supermassive black holes are equally supermassive. Some have millions of solar masses, some have billions, some have perhaps tens of billions, which is mind-boggling, by the way. We're going to talk about some examples of those in a minute. So yeah, keep that in mind. Now I'm going to stop talking for a second and put up a picture because people love pictures. This is an artistic representation of a black hole. You will see this picture all over the internet. It is public domain. There are many variations of pictures like this. The problem with images like this is they don't usually explain the fact that that black ball in the center is not the black hole. That is the gravitational shadow, which exists beyond the edge of the event horizon. We'll be talking about that in a minute. But you're not actually observing the hole. And again, it's not really a hole. Assuming that it's true that black holes are singularities, then of course the singularity would occupy an infinitesimal speck at the center of that gravitational shadow. But the black sphere you're seeing is not the black hole, but rather its gravitational shadow, not the singularity. So you're not seeing the black hole in this image. But the size thing matters in this case because the sphere of influence of a black hole tends to be what we're talking about when we talk about the, quote, size of black holes, when we talk about a big black hole versus a little black hole. This particular one is illustrating one that's pretty big. We'll talk about that more in a second. Notice there seems to be a beam or a jet emanating from its north pole. We'll talk about that too. Those polar jets are very important, and they have a lot to do with the image we're going to be talking about tonight. Okay, so as I said, I'm going to shut up for a second, and I'm going to read some questions. When black holes collide, do they create a meganova, or do they just merge? That's a funny question. I assume you're basing that on the kilonova term that we use to describe the collision of neutron stars. It's a good chance that gamma ray bursts, at least certain types of them, are the result of black hole mergers. So I'm not aware of a word. We have a special word for the explosion of two black holes colliding, but it is, of course, a cataclysmic event, even more powerful than the merger of neutron stars. But that being said, them being so heavy and having such a large sphere of influence, it's possible that you would have less material left over from such a merger because a lot of it could be consumed. But as far as light being emitted, that would be emitted not by the two objects themselves, but the material in their vicinity. And by the way, that's a big part of our show tonight. When you see images or like this drawing on the screen, what we observe when it comes to, and this is very specific, electromagnetic radiation is not that emitted by the black hole itself, but by the material, the accretion disk orbiting the black hole, which is becoming outrageously luminous because it's comprised of material that's being endlessly struck with particles moving at nearly the speed of light. The gravity of the black hole is so intense that it accelerates material to nearly the speed of light, and it is an incredibly, incredibly violent place. Quasars, and I say this in a lot of shows, are among the most luminous objects in nature, and they are the ultra-luminous disks of material being pulled into a supermassive black hole. We're going to be talking about one of those disks tonight. It's a good question. It's a wonderful question. Do photons have mass? If no, why are they affected by black holes? At the risk of going into a massive tangent, in a nutshell, photons can be referred to as massless, and you can say that with a straight face. They have no mass. However, they experience mass equivalence due to the velocity at which they travel through space-time. Because space-time curves due to mass bodies, these photons in their mass equivalents are affected by the curvature of space-time and bend as though they were a physical particle that behaved in the way one would expect a regular particle of mass to behave. So photons are affected by black holes due to mass equivalence, but not because of their individual mass per se. Someone asked about Hawking radiation. This is a little advanced for this part of the show, but I can get through it pretty quick. One of the reasons that Stephen Hawking became such a rock star in physics communities and became a Lucasian professor of mathematics at Cambridge, and of course everyone knows the same position that Isaac Newton held, is because he discovered that black holes are not eternal. Even though it's an object that is completely collapsed gravitationally, it is possible for something very weird, and I'm using that word specifically on purpose, very weird to occur near the edges. In the quantum space-time merged sciences that tend to argue with and fight with each other so much, where we have quantum physics fighting with relativity and classical physics and whatnot, we discover that the universe, in its ability to manifest infinite improbability, will allow for virtual particles to come and go, essentially come into existence and then cease to exist instantaneously. And in some cases, these virtual particles are the result of the existence of real particles. And because there's so many real particles swirling around in a black hole, you have a non-trivial incidence of virtual particles coming into existence. Essentially, one of the particles in the black hole, because of quantum uncertainty, suddenly translocates to a region just outside the black hole, and usually, like I said, disappears. But in doing that, it essentially breaks the rules. It has achieved an escape from an object that has an infinite escape velocity, or a light speed escape velocity, because due to the weirdness of infinite improbability, a particle was here and suddenly it was over here. And so Hawking's figured out, but can you see my mouse? Yes, you can. Hawking's figured out that if one of these virtual particles were suddenly to manifest right here where my mouse is, outside of the gravitational shadow and the event horizon, that particle has essentially achieved a sort of escape from the black hole. And so over unimaginable eons of time, trillions upon trillions of years, a black hole evaporates via Hawking radiation. And by the way, this has been demonstrated to probably be true in many ways, including in the laboratories. So you don't need a black hole to simulate this effect. So yeah, in a nutshell, that's what Hawking's radiation is. The ability of black holes to evaporate as their particles become virtualized by random chance just outside the event horizon and are able to essentially escape. Yeah, that's kind of amazing. And it complicates the whole debate about black holes because it makes it forces us to answer the question of whether or not information is being destroyed. And that's one of the biggest problems with black holes when it comes to physics, this notion that black holes are capable of destroying information. That should be impossible. So we're not going to get into that too much, but that is an interesting topic, and it's worth further study if it interests you, the idea that black holes break the rules in multiple ways, and that's one of them. They essentially possibly destroy information, and theoretically no information in the universe is destroyed. So for a silly example would be when you burn a match, you haven't actually eradicated the match from existence, because all the particles that the match was still exist, although they may have been moved around the room in the smoke or whatever. Some of them may have been converted into energy via the heat and the light, but that energy doesn't cease to exist either. So theoretically you cannot actually eradicate a match. You can burn a match, but you haven't actually caused it to cease to exist. The information of its existence still persists in some form. We assume that is a physical law of the cosmos, that you cannot destroy the match, so to speak. You cannot eradicate or erase or delete the match, even though you may have burned it. That's a silly oversimplification, but it kind of helps explain the concept of information loss in the cosmos, and it's a fundamental tenet of physics. Okay, that was a fun topic. Okay, swirlions. That's funny. Hold that thought. I might get into that. So infinite mass has different gravities. So not infinite mass. That's a good question. Infinite density. There is a difference, isn't there? So you could have two objects of the same mass but very different densities. For example, you could have a piece of foam the size of my desk here, so a huge piece of foam, or you could crush that piece of foam down to the size of a BB. It would be quite dense, but it would not have any more mass. Although the curvature of space-time would be more extreme next to that BB than it would next to my desk, because the material has been condensed into a smaller volume of space. And by the way, that phenomenon is what leads to the runaway collapse, the complete collapse that defines a black hole. Good question. By the way, it takes a lot of mass to do that, to crush something so much that it keeps collapsing. And that's why, when it comes to naturally forming black holes, only the most massive, hypermassive stars tend to become them. By the way, if you guys aren't aware of this, on a basic level, The reason any given star, like for example Betelgeuse or Antares here, do not collapse right now is because they're being held aloft by their radiation output. A star exists on a balance, a knife edge. Gravity wants to crush it, and radiation pressure from fusion wants to blow it apart. The stalemate between these two opposing forces is what defines the radius, if you will, the volume of a star during its life cycle. It doesn't define the mass, it defines how big it's going to be. As the energy output of a star drops, gravity begins to win, and of course the volume of the star will reduce. We're not going to get too much into stellar life cycles, but you can feel free to ask some follow-up questions about that if you don't understand it. Again, this is how black holes form naturally, that is to say, at the end of the life of a hypermassive star. And I want to repeat, these two fellows, Betelgeuse and Antares, will not become black holes. They're not massive enough. Okay, so quasar. Who mentioned quasar? So quasars, I already mentioned, are associated with supermassive black holes that are actively feeding. So let's continue. I wanted to start the show about black holes and then talk about how we imaged it. So let's talk about how we find them for a second. Someone already pointed out you cannot observe a black hole directly because they emit no light, and yet we have our waves. If you're lucky, objects might orbit the black hole, and then all you have to do is clock them, just measure their speed and figure out the mass of the body. This cool chart illustrates the orbits of some stars, and these are their names: S12, S1, S14, S2, S8, S13. These are stars that exist at the heart of the Milky Way galaxy. They are orbiting tremendously quickly, something that isn't there. These stars are orbiting at amazing velocity, a body that we cannot see directly. S2 there happens to be the fastest known star in the Milky Way galaxy. When it's right here at perigee with whatever that thing is that it's orbiting, that star is moving over 11 million miles per hour. What could possibly compel an entire star to go that fast? Almost certainly, in this case, a supermassive black hole. We are not limited, though, to the motion of stars in the case of the supermassive black hole at the heart of our Milky Way galaxy, because the accretion disk, and we talked about those already, we'll talk about them some more, though, because they're important. This accretion disk is highly luminous in multiple wavelengths, including infrared and radio. Radio wavelengths are very good at penetrating obstructions, and we can observe them. Even though this object, let's pretend, for example, that this is our black hole. By the way, its name is Sagittarius A star. Let's pretend this is the black hole at the center of the Milky Way. We have trouble observing it. And by the way, this is part of the show. Keep this in mind. Pay attention to what I'm about to say. Even though it's close to us in our own galaxy, about 30,000 light years away, it's very difficult to observe because we have 30,000 light years of stuff between us and the black hole. Stars, gas, dust. This material blocks light. Radio waves do penetrate these obstacles. And so as a result, it is possible for us to observe the black hole not only thanks to the motion of stars around it, but by radio emissions coming from right there where I'm pointing with my mouse. So there is a strong radio source right there. And by the way, the name of the black hole comes from it's a radio designation. So Sagittarius A star. Okay, so those are the two ways you find a black hole that are reliable. You observe the motion of things orbiting one, if you're lucky enough to find one that is being orbited, or you look for radiation emitted by the accretion disk. Now, it might be a bit easier to measure that radiation if there's nothing in the way. And so, ironically, we're often more successful observing the radiation output of black holes in entirely other galaxies. Depending on where they are in the sky, there may be more or less material blocking our view. For example, probably the most famous galaxy, with the exception of the Milky Way, of course, is the Andromeda Galaxy. Now, this is a visible light image, visible wavelengths. In fact, you can take a picture like this. If you're good with astrophotography, if you have some reasonably good equipment, you can take a picture like this. Now, this image is full of stars in the foreground. Every single star you see in this picture is part of the Milky Way. We're looking through them. This is a good lesson in perspective. When you see other galaxies, you're seeing them behind a curtain of stars that are right here in front of us. And so those stars, most of the stars in this image are a few hundred or a few thousand light years away and part of the Milky Way. The actual disk of the galaxy contains over 1 trillion stars in this case. Andromeda is a very big galaxy. And among those many stars, there are also dead stars, which include neutron stars and black holes. But I challenge you to find either one of those things in this picture. Of course, you will fail, because we haven't, in this case, provided enough contrast, so to speak, to differentiate between these different energy levels of objects. So, we need to employ a different wavelength. I said this is visible light. This is an X-ray image. Now, let me get my head out of the way. What you're seeing here, see this square, is a region of study in the heart of the I almost said Milky Way, the heart of the Andromeda galaxy. And what we see here is changes over time. Notice the dates, January 2012 versus August 2012. We actually see a moment, an X-ray flare, where a sudden X-ray source appeared and then vanished. Something happened. And if you're not sure what, it's pretty exciting. Apparently there was a black hole there, totally undetected. As you can see, there's nothing in the circle here on the 7th of January. And that black hole ate something. Material falling into the accretion disk became ultraluminous, as did the disk itself. It emitted what we call an X-ray flare, and we observed it on Earth. Didn't take very long, only a few months to play out. So that's an example of a black hole that was completely invisible to us, was not observable until it ate something and we saw it briefly. The other bright dots on the image are actively feeding black holes that are probably what we call cataclysmic binary systems, where you have a black hole consuming a companion star. How terrifying. And you might notice that in the core of the galaxy, there's a lot of light, lots of X radiation coming from the core region because, like all the rest, Andromeda does contain a supermassive black hole, which is apparently actively feeding rapidly enough to emit some light, but not rapidly enough to be a quasar. Yeah. So we just talked about the 2 ways you can detect a black hole. Now, and we covered a few things that are important to the second half of the show, which is the imaging thing. Are there any questions so far about that concept of what black holes are and how we find them? Let's hear some questions. I'm sure there are some before we move on. Oh, that's a good question. That's an excellent question. Are radio waves able to withstand black hole feeding forces? No, because radio waves are also light. They're also part of the electromagnetic spectrum. Photons, someone asked about why they're drawn in. So no, just like all the other parts of the EM spectrum, radio waves cannot escape the black hole directly. But if they're emitted by material near the black hole, but not beyond its event horizon, then even radio waves can escape. That's an extremely good question, and it does apply to the show tonight. Because I should point out, even though we're about to talk about a picture of a black hole, it's not actually that. We took a picture of the vicinity of a black hole, the immediate vicinity, its accretion disk, and the gravitational shadow created by the black hole, but not the black hole itself. Good question. Here's something fun for you, just for funsies' sake. Watch this. This is real data. This is infrared data, not radio, from the core of our galaxy, the Milky Way. Notice the date. This is old data from 1995. We're going to move through time. Watch this. So what was that last date there? 2010. So we're going from 1995 to 2010. Look at the difference. Notice the yellow star there, the one near the center. That is S2, the fastest star in the galaxy. So it takes about 15 years, or a little bit less, I think, for it to complete a single orbit. That's pretty impressive. Questions about that? Good question about the radio waves. Okay, now we need to start talking about the picture that changed everything. Picture that changed the world. This is it. I'm actually going to, just for the sake of gravity, I'm going to get my head out of the way so you can appreciate its awesomeness. This is the first ever image taken of a black hole. But for me, it's not the image that's impressive, but the backstory, and that's what this show is about tonight, explaining how we did it. Because this shouldn't be possible. And you're going to learn about why that is in a second. Before we go over why it's impossible and how we did the impossible, let me look at the chat again really quick. Will the Webb telescope impact our study of black holes? Oh, definitely, because it is an infrared telescope, and it will allow us to study structures like this, the accretion disks of distant black holes, in very distant galaxies. James Webb will essentially be able to see all the way back to the beginning of space-time. It will be able to see the immediate aftermath of the black hole, of the Big Bang. Partly because it's just so big, and also because it's infrared. Infrared wavelengths end up being a lot more important in this context quite often than visible wavelengths, because they're emitted by things that are not just hot, but warm. By the way, not everything in the universe is blazing hot. So you can't expect everything to be luminous in visible wavelengths, because for something to be that, it has to be pretty hot. Not everything is that hot. So infrared allows you to observe things that are warm but not hot, and it's able to penetrate barriers better than visible light, for example, or higher energy wavelengths like ultraviolet, X-ray, gamma ray. So that's even more true in the case of radio waves, which are lower still on the spectrum. Bigger waves, larger wavelength. Radio waves are even better at penetrating obstacles than infrared, and because they're lower energy waves, are emitted by less energetic particles. Even stuff that's relatively cold emits radio waves. I like to joke about this. If human beings could see radio waves, if we could see radio, the world would be a very confusing place, because you discover that everything was emitting radio waves. Stuff like a door hinge, like the wind is blowing the door a little bit and the door does that, squeak, squeak, squeak. You don't realize that the hinges of the door are going to be emitting radio waves, and because they're being excited, the atoms are being excited by the interaction. And it would be like the door hinges would be flashing at you every time that the door moved a little bit. It would be very spooky. A person would be glowing, and there'd be flashes of light coming out of their brain, and their feet on the floor would be flashing because of little static discharges between their feet and the floor. Yeah, so the universe in radio is very busy, and that's because it doesn't take a lot of energy for something to emit radio waves. Yeah. So James, just so you know, of course, James Webb is not a radio telescope, because it doesn't need to be. We can build very large telescopes on the ground that detect radio waves, and that's actually part of our show tonight. This is the FAST reflector, currently the world's largest telescope. This is in China. It's bigger than Arecibo, may she rest in peace. And this is not a tangent. Why is this telescope so big? I think it was over 1,000 feet wide. Why is this telescope 1,000 meters? What was it? I should know that. Why is it so big? Why do we keep making larger and larger? In this case, it's a radio telescope, but it doesn't have to be. Why do we keep building larger and larger telescopes, guys? I'm going to let you answer that. While you do that, why do we build big telescopes? Yeah, 1,006, is it 500 meters? Yeah. So 1,640 feet wide. That is the size of that telescope in front of you right there. Okay, good. So Ed got the answer right. Resolution related to diameter. So this is, by the way, not the most common answer. The most common answer you get when you ask about why do we keep building bigger telescopes is because people understand correctly that we want to collect more light so that we can get images of dimmer things. That's true. But as Ed points out, there's a direct relationship between size, diameter, and resolution. And that's very important when it comes to what we're going to talk about tonight. Also, someone points out, and this is very important, the wavelength of light you're studying also directly affects resolution, because literally the larger the waves, the less photons you're going to collect over a given surface area, and the less sharp your image. The smaller the waves, theoretically, the more you will collect more photons you will collect over a given surface area, and the sharper your image. The equation to work this out is very simple. Let me switch back to my faster view. So this is how you do it. If you want to figure out I like this, by the way, I use this because I like the term angular separation, which is better than angular resolution, because it reminds us that for you to obtain new information about a target, you need information from other locations on that target, so to speak. So the more separation you have between data points on a given object, the more resolution you have by definition. I believe this particular equation using that 1.22 metric is based on arc seconds, which is a very tiny measurement of diameter, angular diameter in space or anywhere. And as you can see, That value is based on that number multiplied by wavelength of light you're trying to observe divided by the diameter of the mirror. We're not gonna work this out for you right now. I just wanted to show you that the mathematical relationship between wavelength, size of optic, and resolution is very, very well known. And this equation can be applied to the design of a telescope. And the design of that telescope is going to be based around what you're trying to look at, where you're trying to see it, what wavelength of that object you're trying to observe. And this informs our decisions. This is a very big part of our show tonight. Now, let's we got. Can resolution also be increased by pairing radio telescopes around? Well, it's funny you asked that because yes, that is one thing that we do. Before we get into the radio pairing, let's talk about one that doesn't get enough press, Keck. So the Keck Observatory in Hawaii has two identical telescopes, and they're very big. These two telescopes, and by the way, let me show you just how big. If you look at the, let's see. If you look at that car there, look. There's one of the telescopes, and look, there's looks like a Nissan Pathfinder or something like that. Parked, maybe it's a Jeep. So that's parked next to the dome, and you can appreciate how large this is. So each one of those telescopes is 33-foot diameter. They're identical, and they're spaced apart about 280 feet. Now, what's remarkable about this is by using these two telescopes in this clever way, we can simulate the effect of a telescope with a 280-foot diameter mirror. However, it's not a round mirror in a virtual sense that that mirror, that artificial mirror, or that synthetic aperture may be 280 feet wide, but it's only 33 feet tall. So essentially you've created a cylindrical telescope that's quite wide, but not very tall. That's going to come up very strongly in a few minutes when we talk about the challenges of what we did to take that picture of the black hole. Now, this is an unusual or rare example of an optical wavelength interferometer. We talked a little bit about interferometers in our last few shows ago, actually. And I want you to understand how it works. In a nutshell, if you collect two waves that are the same, that is, so wave A and wave B are the same, in this case, phase angle, timing interval, we are, in this case, saying that the two waves are in phase and they increase the final output. So by gathering, let's say, two photons oscillating in the exact same way, you've achieved, let's say, a brighter image. You have more gain. You have achieved higher luminosity. However, you have not actually gathered more information, because resolution is not just more photons, it's more photons which are different from each other. So let me give you an example. Watch this. I have this ball here. Be very careful with it. There you go. For the viewers at home, I think you would all agree that this ball was white. However, if someone was sitting over there, so away from the camera, they would see the ball like this, and they would say, oh, look, it has a black edge. Similarly, if someone was sitting over there, they'd see it like this. Oh, look, I see a black edge. Simply put, if you want to achieve more information, if you want to collect more information about an object, it's important that you have a greater number of perspectives on it. You literally simulate this with a larger telescope, because if you have a lens this big, you're going to be collecting light over here, and you're going to be collecting light over here, and you're going to be collecting light here, and everything in between. But if the lens was this big, big as the whole circle my head is in, you'd be getting more photons from different perspectives. Theoretically, you'd be getting more information. Do we understand that basic concept? If you don't, please ask questions, because it's kind of important. It has everything to do with our show tonight. Do you understand that to get more information, you need more information that is different? And by increasing your number of, let's say, points of observation, increasing the distance between them, you're maximizing the opportunity to collect new information. Now, someone asked about the VLA. Hold that thought. I'm going to read the chat really quick because I want to make sure you guys understand this. Yeah. Yeah, so someone points out it should make 6 domes to get closer to round synthetic aperture. That, again, is going to come up directly. That's actually a huge part of the show. The problem with the Keck design, like I said already, is that it's creating a synthetic aperture of a tubular telescope. Essentially, it's like a tube. You would want more telescopes filling in the gaps to create, like someone points out, a circular synthetic aperture. We don't always have that luxury. That can be an expensive thing. You know, you don't have the money to build more telescopes. It can be a geographic problem. There's no space to put those. However, we have certainly tried. So, someone points out this famous thing, the VLA, the Very Large Array in New Mexico. It's a very clever machine because you have multiple giant radio telescopes that exist on a track. They're actually on train tracks. See the train tracks? One can, let me see, there we go. One can relocate these to different places, different distances apart, to achieve different goals. This is pretty cool. This is a drawing of their layout, and we've listed information here about 4 different configurations of the Very Large Array, configuration A, B, C, and D. And this is essentially the effective, in terms of kilometers, diameter of the synthetic telescope, the synthetic aperture. So as you can see, configuration A is the widest, 36-kilometer synthetic aperture. D is the narrowest, only 1. Of course, some of you might be saying, well, why would you do that? Why wouldn't you just build them all in configuration A and leave it that way forever? Because by spacing the collectors apart, farther away from each other, you are effectively increasing resolution, but you are decreasing gain because you have less collectors in a forgiven square footage of size of synthetic aperture collecting effectively less photons for a given amount of information. So essentially you're collecting less photons. Even though you're collecting more photons which are different from each other, overall you're collecting less photons of a given, let's say, feature on the object. And so the image will be dimmer, and so you must employ a longer exposure. Or you must be content with having less information, but having good, sharp information from what you do manage to collect. For example, so what we have here are 4 images taken of an active galactic nuclei. So we have a quasar that is actively consuming material. It is a supermassive black hole there, consuming material. Not only do we see the luminosity of the accretion disk glowing as a little point, we also see vast plumes of material escaping the black hole along its north or south polar electromagnetic axes. What you notice is that in configuration A, we have a very sharp picture. Configuration D, we have a dull, low quality, low resolution picture, but also notice we also have more information because we were able to collect dim light that was completely lost due to the lower gain of configuration A. And some of you might be asking, well, could you combine these things? Of course, and that's what we do. So you'll run the telescope at different resolutions to collect either more information or, in this case, more gain. I think that's pretty cool. Yeah, look at that. Trade-offs abound. I agree. That's totally true. Hey, so Jim says he's been there. Very impressive, yeah. Very clever machine with a very non-clever name. The Very Large Array. Yeah, but see, if you create the acronym, it sounds high-tech because everyone knows acronyms are synonymous with science. So VLA, I'm sure that stands for something really deep and powerful. Here's 3 more examples. Same concept. We have an active galactic nuclei with a jet. We only have 3 examples here, not of all 4 configurations. Notice the bottom picture is very low quality in terms of sharpness, low resolution, but excellent gain. It allowed us to collect data about material in the vicinity of that jet. Now, are there any questions about that let's use the term trade-off, between size in terms of resolution and size in terms of gain? Let's hear some questions now if we don't get that, and then we're going to move on to the really exciting stuff. Now, an interferometer, hold that thought, I'm going to clean up my desktop a little bit here. An interferometer makes use of destructive interference to tease out hidden difference in data. So let's pretend that wave A and wave B on the side here, destructive interference side, are being collected by different telescopes in the very large array. Their information they're collecting is exactly out of phase with itself, so it's 180 degrees out of phase, and of course the final result is nothing, because these two identical but out of phase waves have canceled each other out. They've nullified each other. If there were some anomaly, let's say information in wave A here, where my mouse is, but not on wave B, then a little spike would survive right where my mouse is here. You'd see a little bump. That would be new information that may have been otherwise lost in the data. Interferometers can tease out subtle, difficult to detect data by comparing almost identical, but not exactly identical waveforms. This is how it happens. This is how you increase your resolution, by increasing the angular diameter of your synthetic aperture system. Notice that I keep saying that word, synthetic aperture, because we're not actually creating a telescope as big as the very large array's diameter, but we're pretending we are. Of course, making any useful data, getting anything useful, any context out of this data, is of course the work of computers. That being said, the Very Large Array was constructed in the 1980s. Computer technology was insufficiently fast at that time to process the overwhelming amounts of data coming in from the radio telescopes to perform this cancellation routine. As a result, this is done organically, let's say naturally, because beneath those train tracks on the Very Large Array are pipes known as waveguides. So pretend underneath the train tracks you have these metal tubes which actually bounce the radio waves from the collectors down so they converge in a single collection point. We're allowing the radio waves to do the cancellation themselves, so to speak. We're not letting the computer see the data until that analog data has already managed to interfere with itself. On one hand, it's extremely elegant, beautiful even, because it's doing this passively. On the other hand, it's primitive, because it requires us to find a way to very precisely and very cleanly guide the radio waves to a single place, and of course that is very difficult. It's also very limiting, because let's say you wanted to make this thing 1,000 miles across as opposed to 1,000 meters or whatever. Well, guess what? You're not going to be able to do that, because you'll have to bury literally thousands of miles of waveguides. Same exact thing is true with the keck. I showed you the picture of the keck. Let me show you a drawing of it. I apologize for the crudity of this image. It was a scan from a book, and I have yet to find a better quality picture of it. Someone did a bad job scanning it, and it's badly rescaled, but we can kind of read the labels here. Let me zoom in a little bit. Notice keck 1, keck 2, we have this room. Look, we got control room, computer room, office, very important room, that's a very important room. Storage, even more important. Machine shop, so they can do their own custom repairs. Luminizing area, that must be for fixing the mirrors. Oh look, another office, another computer room, another control room. So as you can see, they're mirror images. But then we have this important chamber beneath the structure. Check it out. Beam confining room. This is even more true with Keck than it was in the Very Large Array. Keck is an optical wavelength telescope, and also I think a little infrared. And so, even more so, computers cannot crunch the numbers fast enough to perform real-time interferometry on this data. So once again, we employ a passive cancellation system, an analog system, where light collected from Keck 2 and light collected from Keck 1 is able to interact within prisms and other optical systems. I tried to find a picture of that. I couldn't find it. It might be a little secret. I'm not sure. But it very impressively allows this light to interact with itself, and just like I showed you with that chart, cancel itself out. It allows us to prize hidden data or difficult to find data from almost identical but not exactly identical signals. Once that has happened, once that passive process has occurred, the computers get a hold of it and they can do further processing. By the way, this is not about what we're talking about tonight, and yet you need to understand this backstory a little bit before we talk about the main event. Are there any questions about that? Gotta love analog computers. I wouldn't call it an analog computer. It's connected to digital computers, But the processing is done in analog, I guess you could say. But it's not a computer process. It's an optical process involving light rays bouncing off and interacting with each other inside of some kind of glass or quartz chamber. Okay, now, we've spent an hour talking about black holes and observing them. We haven't got to the main event. Ironically, it's not going to take that long to do that. Before I do it, though, I want to make sure we have no unanswered questions about this concept, this notion of interferometry before we do the big thing. Okay, now, the very important one. The M87 black hole. M87 is a galaxy in the constellation Virgo. It is an exceptionally massive galaxy. It's an elliptical galaxy. And it is one of the largest and most luminous galaxies in the Virgo constellation, and so we often nickname M87 the Virgo galaxy. Here's a picture of it. Now, what's cool about this picture is, and you could take, by the way, again, you could take a picture like this at home. I believe this is an amateur photograph. I don't think this is a professional image. Let me take my hat out of the way. You could take a picture. How is the focus image transfer to being combined without making it? Well, so that's an excellent question. Let me pause on that for a second. So Ryan O'Connor is asking, how are you passing the beam through many feet of tubing without losing focus? There's many ways. First of all, the actual effective focal length of the instrument is extremely long and will take that focal plane well into the mechanism, deep into the mechanism. But then there are optics like telecentric converters, which will collimate the rays of light, which would ordinarily be converging due to being focused by a curved optic, and instead go in a straight line, kind of like what a telescope eyepiece does, or even a camera lens. So if you place that optic in the right location in the imaging train, it will collimate the rays of light, and they pass in a straight line, almost like a laser, but not quite. And so they will pass down these chambers without losing focus. By the way, for a system like that to work, you need outrageously high-quality optics, which have to be absolutely meticulously installed, maintained, checked, collimated, calibrated. That's a maintenance item. And so there are people that work in observatories like that, and that's their job. Their job is to make sure all those many optical systems, those optical pathways, those optical elements are all working in agreement with each other. Because if they don't, the whole thing don't work. So yeah, by the way, that's one issue with passive interferometry, because you have to construct this very clever apparatus that has to be performing essentially perfectly, or else it doesn't work at all. There's really no margin for error there. That's a good question. Yeah, so Ed points out relay lenses. That's right, moving the focal plane. Making it telecentric is part of that equation. You have to make the rays go in a straight line. Or design a really huge chamber, and they did not do this with Keck. But I suppose you could do that without those optics, but you'd have to have I don't even know how you'd do it, because the pipe or tube would have to move with the telescopes. Of course, the telescopes have to move, don't they? Okay, now, this image of the Virgo galaxy, I like this picture because you guys see stars in the foreground, like this big bright one here. This is obviously a very nearby star. We see other galaxies in the Virgo cluster. It's a very busy cluster of galaxies. And then you see this, what looks like a glow. This glow around the Virgo galaxy is not a glow. That is stars. So this is a gigantic elliptical galaxy with multiple trillions of stars. And millions plural, of light years across. But we're not interested in the whole galaxy. What we're interested in is the core of the galaxy. Now, if I zoom in a little bit, you're going to see something. You might have already spotted it. You guys see anything weird in the picture yet? I could zoom in more, but before I do, I want to see if you guys can find it. Do you see anything weird in the picture? I'll get a little closer. Let's answer the question. Anything weird in the picture, guys? Good, that's true. What Jim says is true. If you take a telescope, even a relatively low power, and by the way, actually, especially a low power telescope, and you point it in Virgo and move around, you will be shocked at the number of galaxies you will see. It is an incredibly dense galaxy cluster. Okay, someone says flare. Jim says a jet, and Alex says jets. That's the word, right. We're seeing Let's do, and I'm glad you said the jet, Ed, because it's not jets, plural. There are two jets, but in this image and many images, you can only see one of them. So yeah, that line you see, that is a jet. In fact, it's a relativistic jet because it's comprised of material that is moving at nearly the speed of light. That jet tells us something. Let's see if you can figure it out. What does that jet tell us about the black hole at the center of M87? What do you think? What does that jet tell us about that black hole? This is, by the way, a big part of the show tonight. Why does that jet matter to us a lot? It is feeding. Very good. That's right. Exactly. So it tells us that the black hole is actively feeding. And by the way, not just kind of nibbling, but truly devouring mass. And enough that it has an extremely obvious jet comprised of material moving at nearly the speed of light. Good. Black hole is an active nucleus, active ATM. I think you mean AGM, active galactic nucleus, or AGN. So, yeah. So that's interesting. Maybe we should study it. But upon study, we find some other extraordinary and exceptional things. We find the Doppler shift of the starlight from the core region to be such that the stars are moving at such extreme velocities that the black hole apparently has an absolutely mind-boggling mass. By the way, it's over 6 billion, with a B, 6 billion solar masses. So that black hole is definitely of the supermassive variety, over 6 million times the mass of our sun. Compare that to the black hole at the center of our Milky Way. It's 1,000 times heavier. The black hole at the center of our Milky Way, Sagittarius A, is about 4.5 million, not billion, 4.5 million solar masses, which is still pretty darn impressive, pretty darn mind-boggling, and yet not nearly as massive as the one in the center of Virgo. The Virgo galaxy's supermassive black holes is one of the most massive in the local universe. Now, that word local is quite a stretch because this galaxy is not nearby. What is it? I should remember that off the top of my head. It's 54 million light years away. Hold that thought, because I want to get that real quick. M87 galaxy distance. Yeah, that's right. So 53. So 53.5 light years. It's almost 54. 53.5. Let's just say 53. 53 million light years away is considered close in this context because many of the active galactic nuclei that we observe are within galaxies that are literally billions of light years away. Now, and what I'm doing right now is making a list of reasons we might want to study this galaxy. So we know that the black hole is feeding. We know that the black hole is extraordinarily massive. We also know that it's close, air quotes. And then there's something very basic, and I'm going to show it to you. This might interest you. Let's go to the stars. The sky over Milky Way. Sky over Goldendale. My brain tonight, my goodness. All right, this is the sky right now. Let's go over to Virgo. There she is. And I'm going to lock on to M87. Okay, you see the little target there in the middle of the screen. That's where M87 galaxy is. As you can see, it's near the border with Coma Berenices. There it is. And you can also see some of those companion galaxies, part of the Virgo cluster. Now watch this. I'm going to leave that target on the screen, and I'm going to zoom out to an impossible amount. So this is far more than you could ever actually zoom out in real life because you don't have fish eyeballs, you don't have giant basketball-sized eyeballs sticking out of your head. So you wouldn't be able to see the whole sky at once. You can see the Milky Way as a ring which surrounds us, can't you? Now, let's see if you were paying attention. This has some bearing on something we talked about earlier in the show. Notice, if I zoom out to a ridiculous degree, completely ridiculous, impossible now. This is a field of view that you could never achieve in real life, even if you were floating in outer space. I suppose maybe if you had like a spherical lens and you were floating in space, you could see a view like this. Let's see. How would you describe the location of M87? And again, remember that we have the target right there. Relative to the plane of the Milky Way galaxy. How would you describe it? What do you think? Oh, by the way, Glenn Mars asking about the jet being fainter. hold that thought, because that's actually very important. That detail is actually going to come up. So yeah, remind me if I don't answer it. All right, so how would you perpendicular, center, I like these answers. Essentially, it's straight up, so to speak, above the galactic plane. Why does that matter a whole bunch when it comes to studying it? What do you think? Why do we love that? Why do we love the fact that it's essentially directly above the galactic plane? What do you think? Perpendicular-ish, I like that. And you're right, it's not exactly there, but it's close. Let's see if you guys can understand this. Why is it a huge deal when it comes to selecting an object of study? Virgo is not obscured by any of the Milky Way disk. That's right, very good. The densest part of our galaxy, the disk, because of course we live in a spiral galaxy, is where all the stuff is. That's why it's the densest. And that makes it difficult to study. Yeah, someone says fewer stars in the way. Very good. Not just stars, also gas and dust. Right. So on that subject, I've always found this amusing. Astronomers have a pet name for that beautiful band of light that we so enjoy gazing across. Astronomers refer to that band of light as the zone of avoidance. And we call it that because we avoid studying objects within the zone because it's so challenging and frustrating, because you have to delete all the spectra of all this intervening material between you and the target. That's a huge time sink, by the way. You can do it. You can study objects within the plane, beyond the plane, but it takes a lot of time because you have to delete all that data. There are some astronomers who specialize in that. I salute those fellows because, my goodness, what a lot of work that is. Yeah, so essentially as far away from the plane as you can realistically get. So what I've done here, I've just created a list of the reasons why this particular object was chosen for the experiment that we're going to talk about next. Before I get to that, and by the way, that'll be the end of the show when we get to that part, the most important part. Before I do it, are there any questions about what I just said? Yeah, diameter of Milky Way can be an aperture of synthetic telescope. That would be very challenging. We would need to be outside of our galaxy. Now, it's funny you say that, though, because you could use another galaxy for that purpose. Gravitational lensing can, believe it or not, increase resolution of study, because as light is bent around the galaxy, light coming from over here, for example, is going to be different from over here. Essentially, it's exaggerating or amplifying the difference. So yeah, believe it or not, you can create a synthetic aperture galaxy telescope, but not our own galaxy because we're inside of it. How would you communicate with those telescopes? You know, that's funny. All right, we're finally down to the part where we talk about how we did this. So within the heart of that galaxy is this object. Now, I need you to understand what you're looking at. I got a cool picture here of the comic strip XKDC. Actually, is that how you say it? They did a cool thing. They overlaid the orbit of Pluto on top of this image, so you could understand the size of it. So this is an accurate overlay that shows you a few things to help you comprehend the size, the scale of what you're looking at. So we have the sun, we have the orbit of Pluto. Let's pretend we're like little kids back before Pluto was demoted. A lot of us kind of in our heads pretended that Pluto was the mile marker for the solar system. Like once you were there, you were leaving the solar system. Of course, we know that's not true anymore. We know there are objects far beyond Pluto, far, far beyond, that still orbit the sun. I showed you one Sedna in that chart a few minutes ago of orbits of the black hole in the center of our galaxy. So, again, using our childhood imaginations for what we determine to be the size of our solar system, Pluto kind of defines that. And then we also see the Voyager 1 space probe to help you, again, appreciate the size. This is also accurate. So what you're seeing here, depending on your point of view, depending on your perspective, is how big or small this region of space is. But I'm going to go with small in this context, because you might remember I told you that the M87 galaxy is 53 million light years away. So even something as big as our solar system appears relatively puny. In fact, this image represents, and I'm going to borrow an analogy from Katie Bauman, one of these computer scientists on the project, because I think it's a pretty good analogy. You're looking at a patch of sky in this case, about the same size as an orange sitting on the surface of Earth's moon. So imagine trying to take a picture of an orange from Earth's surface. I think you would agree that's impossible, because how could you achieve such resolution? In fact, you couldn't, and there's a few reasons why. One of them, though, that we don't talk about enough is Earth's atmosphere. If you were to employ visible wavelengths, that is. You see, Earth's atmosphere is a serious impediment to, in this case, visible observation, and infrared, and ultraviolet, and X-ray, and gamma ray. However, Earth's atmosphere does not effectively block radio waves. And so one can construct a giant telescope on the Earth's surface and achieve good radio astronomy, despite the presence of Earth's atmosphere, because, again, radio waves are not stymied, almost at all, really, by air. Of course, you know this because you own devices that use radio waves, and the air itself is not the reason why you have signal issues. And by the way, also buildings. I'm sitting in a room right now, and I have full bars. Of course, some of you might not know there are 2 cell phone towers directly next to the observatory, so that does help. But of course, most of you know that you, of course, can use your phones indoors. So radio waves can penetrate other obstacles too, not just air. Okay, so when we do the math, when we plug in the equations, and by the way, if you don't remember, it was this equation. It turns out that you need to construct a telescope the size of Earth itself in order to achieve sufficient angular resolution to take a picture like this. So in other words, impossible. Some of you might already know where we're going with this based on the setup. You can create a synthetic aperture, perhaps. Create an imaginary, a virtual telescope that appears or behaves like it's the size of our planet, but of course is not actually that big. It simply points on a big planet. So I'm reading this now. Okay, yep, good. Enter the Event Horizon Network. Wow, my head is in the exact worst spot. There you go. Now, if you're wondering what the colors mean, yellow and blue, that has to do with the different networks. This is not all of these telescopes are part of just the Event Horizon Network, but the blue is. So, and by the way, they share data from the yellow ones. So, as you can see, we have a number of radio observatories scattered across the planet, and they are essentially acting like an Earth-sized interferometer. Yes, now, this is where we get to the wet blanket phase, though. It's very tempting to pretend that you've essentially created this, that you've made a giant oval dish the size of Earth. It's tempting to say that, but you haven't really done that. The lines in these drawings are very important because these lines illustrate the different modules, if you will, the different nodes that were used as essentially 2-point interferometers. So again, we have the problem of the tunnel effect, the tube. So we have a tube of fantastically wide resolution, but fantastically narrow, let's say, vertical resolution. Let's use that. Let's be somewhat soft or reckless with our words. It's the width is great, but the verticality, the height is poor. So as a result, you will be getting images of the sky which look like slices of sky. And you can't really just take a bunch of slices and get a good picture out of it. Here's the problem. A computer, and not just a computer, an artificially intelligent system, needs to take those slices and it needs to figure out what could be possible. Essentially, it needs to determine what kind of image could exist based on the data. Now, the computer scientists create a simulation, feed it in of what they think it might look like, feed it into the algorithm, and see what it spits out. Now, some of you might already be crying red flag because it sounds like we just gave the computer program a predetermined outcome and it needs to get there. Hold that thought because that's very important. First of all, really? Hold on. As I was saying, if we're going to try to reconstruct an image that we think, very important words, we think resembles this one, based on data taken by all these individual points, I will first tell you that we have some good news. Notice that we don't have actual straight lines. We have these arcs because even though the telescopes occupy specific places or points on Earth, Earth itself rotates. This is helpful. It's like a scanner. You move the scanning head over the object you're scanning. So Earth itself rotating improves dramatically, by the way, the amount of data that these telescopes can collect, because essentially we're scanning their field of view over the cosmos, in this case scanning them over the object. Unfortunately, though, with all these cylinders of observation, we get a very large, and these word here, infinite number of possibilities as to what the image might look like. For example, the image could look like random noise, or it could look like this, or that, or that. So we keep feeding the algorithm data over literally months of time, and we keep improving the quality of the simulation. And we do things to start making sure we're not interjecting bias into the system. Check it out. We start feeding the algorithm deliberately incorrect pictures, along with correct pictures of astronomical objects that we expect to resemble what it should be seeing, and space objects that don't, but they're space objects. The idea here is that you're feeding the imagination of a machine learning algorithm with all sorts of information, and you're waiting for it to make a mistake. If, for example, it spits out an image of a black hole and it looks like this guy's face, or this kitten, or this elephant, then obviously we know that we have, unfortunately, injected bias into the algorithm. And so the image we're getting is not real, so to speak. It is a version of reality tainted or tinted or colored by the information we fed the algorithm. Here's the good news. When they do this, we get very similar images. This is fantastic because it shows that the machine learning algorithm is discriminatory enough with its data that it's not being led astray, so to speak, by junk data. So notice that we have an image with our simulations, looks like that. An image with our astronomical objects, looks like that. And even the one with the goofy pictures of people and elephants and cats, looks like that. This, in a nutshell, and by the way, we're oversimplifying this a lot, this is the machine learning process. This is how we make sure that it's not spitting out what we want it to spit out. By the way, the physicists that work on these projects, they're not dummies. They know that machine learning is in its infancy and it's evolving quickly. We know that artificial intelligence is new. We know that it can make mistakes, and we're deathly afraid of bias. We're afraid that the machine is going to behave like its programmers intended it to, even if they didn't want to inject intent, just because human beings invented this thing, and human beings have their own experience, and they might say, machine, this is how you figure out that thing. This is how you compute this. When you see this type of vector, you should create a parabola like this one. When you see a point source like this, you should extrapolate that as a rectangle of this. You add all these little provisions, and before you know it, you've taken your AI and you've turned it into a robot. And there is a difference between robots and AI, because a robot is a machine that does exactly what you tell it to. Widget A goes into slot B. When input 3 happens, output 7 should occur, that kind of thing. AI is far more sophisticated. We talked about this a lot last week, so I'm not going to rehash it all. But in a nutshell, an AI system has the astonishing ability to retool itself to the problem. In this case, the problem we're trying to solve is data that is incomplete, because our interferometer is giving us this swirly pie slice of the universe, or in this case, an object. And we need to fill in the gaps. Before I continue, are there any questions about that? I made the joke earlier about the fact that I was being accused of a typo with the word imaging. And they thought I meant imagining, but I didn't. Although in a way it is true, because we are literally talking about the imagination of a computer. It is looking at what could be true, weighing it against the data, trying to determine what could not be true, and over literally billions and billions upon billions and billions and billions of calculations, it spits out a very, very well considered, very heavily thought out form of imaginative imaging. Questions so far? AI is more than a state machine. Do you mean slot machine? So it can fill in the gaps. What's funny though is it sounds outrageous that we're talking about a picture which is kind of a figment of a computer's imagination, but it's not so outrageous when you consider the fact that theoretically a computer should be much better at this than we are, because it has perfect total recall. It won't forget things. I remember when this thing looked like that thing. It won't forget that. And of course, it can save all of its outputs. And so over time, we get this iterative, increasingly improved, increasing resolution, evolving image. And by the way, the image that we saw, the one that was so famous, that wasn't the final story. They kept reprocessing it. They also processed old data used by, let's say, sourced from a smaller number of observatories. And what's interesting here is that we also discover, even though we have very low quality images here in the earlier stages of the project, we see that this black hole disk is changing. We see that it is evolving. That's very interesting. And of course, it's because it's rotating, right? That's part of it. As you can see, as we increase the number of collectors on the circuit, so to speak, the network, you see a better quality image. Okay, questions. I have more to say. I'm almost done, but other questions so far? Let's go back to this picture. Let's talk about why this picture is such a big deal. First of all, even after ruling out bias, it's very exciting to point out that the image ended up resembling what they thought it might. And what's neat also is what they thought it might resemble was based on relativity. Because one of the reasons you want to take pictures of black holes is to see if they behave the way they're predicted to behave. Before this picture, all of our understanding of the surroundings of a black hole, of the environment that a black hole exists in, were based on simulations, based on theory that were worked out in increasingly high-quality computer models, but they were still models. We needed a picture. So what's exciting is that the image resembles what we thought it might. So let's talk about why it's a big deal. First of all, I need to point out that the darkness here is not the black hole. And I want to repeat something I said earlier. It's not really a picture of a black hole, is it? We're looking at the accretion disk around it and the gravitational shadow. Now, the gravitational shadow is not the same thing as the event horizon. Someone asked earlier about whether or not radio waves could escape a black hole, and I pointed out no. They could, as long as they don't cross the event horizon. Like anything else, the event horizon is referred to as the point of no return, where the escape velocity becomes greater than c, which is the speed of light, of course. So if you cross the event horizon of a black hole, you have to go faster than light in order to escape. The gravitational shadow is actually larger than that. And by the way, it's not a coincidence that they chose to use Pluto's orbit. It wasn't just because we're used to using Pluto's orbit to describe the extent of our solar system. It's also because that is roughly where we think the event horizon is. And by the way, that is horrifyingly, humongously gigantic. It is hard to imagine an event horizon that big. We're talking about an event horizon, a point of no return, as large as our solar system. To give you some idea of how unusual that is, a stellar mass black hole might have an event horizon significantly smaller than Earth's moon. I remind you, black holes are not the ravenous cosmic eating machines that we see in the movies. In fact, a black hole could pass through our solar system and we might not even notice it because their sphere of influence is surprisingly tiny. The only reason why they seem to have an outsized influence on the universe is because we sometimes catch them in the act, in this case, of drawing in huge amounts of material, and then, of course, they're more noticeable. But the actual black hole itself is theoretically zero volume, and the event horizon is tiny, maybe the size of a large mountain, for example. Think about that. However, supermassive black holes are no ordinary black hole, and they do have event horizons that are gigantic, the size of a star system. Keep that in mind. Think about that if you have any questions. Ha! Hey, that's a great question. What is the shutter speed of this image? Months. It's months of data. Although, to give I think when they were trying to take a picture of a snapshot, it was a few days. I think it was like about a week of observing sessions from different telescopes. And by the way, I learned something doing some research. Very often it was only a few hours of data because of all kinds of things, the realities of everyday life. For example, one of those telescopes being on the South Pole, they had electricity problems, and they had freezing issues with equipment and all kinds of things, and that cuts into your observing time. So let's say about a week of combined data, roughly, and then a lot of months of backup and follow-up data. Now, we learn something exciting. Notice that the image is not uniformly bright. There seems to be a brightness here, what we call a luminosity enhancement. That is not because that part of the disk is actually brighter. It's because of a phenomenon known as Doppler boosting, or what I like, the more fun one, is relativistic beaming. So essentially, material emitting light, if it's being thrown at you at enormous speed, that will actually artificially brighten it, its appearance, because the photons pile up. And of course, this doesn't normally happen. Only stuff that's moving at speeds very close to that of light will experience relativistic beaming. But then on the top of the disk, we see the opposite. We see anti-beaming, where the Doppler, in this case, shift is not boosting but retarding the light output. So it appears dimmed artificially because the material is moving away from us at such great speed that it's artificially reduced in luminosity. So right there, that was a phenomenon that was predicted to occur, but we didn't know if it would. Questions about that? Now, this goes back to something I said earlier. I said that there's only one beam or one jet. There should be two. We have confirmed that there are two jets, which, by the way, is completely expected. It would be actually weird, bizarre. It would actually be inexplicable, even, if it only had one jet. But the fact that it only appears to have one is because of the same phenomenon. This material is coming towards us at nearly the speed of light. And so, again, we have that Doppler boosting or relativistic beaming effect. Meanwhile, the material moving away from us at nearly the speed of light appears artificially dimmed because of the way it's moving away from us. Questions about that? Now, there's a few other things. They weren't sure how this was going to look. They weren't sure how big the shadow was going to be. They thought the shadow might not exist. They thought it might be 3 times bigger. We had predictions based on our understandings of what we thought material would do near a black hole. And hey, it worked out. Again, the radius of the entire structure, the radius of the gravitational shadow, turns out to be the size they expected it to be. And it also perfectly, or almost perfectly, very close, very tightly, works out to the correct mass for the black hole, which is over 6 billion, with a B, solar masses, yeah. A big triumph for science. Questions about that? Let's see, we talked about this Event Horizon Telescope. And we talked about the fact, how far away. So this is, like I said, this is in the M87 galaxy. So it's 53 million light years away. That's how far away this is. And by the way, for me, mind-boggling that we can take a sharp image of something that's only, and I'm being serious when I say only, something as small as a single star system at that distance. This light took 53.5 million years to reach our planet. That's how far away this galaxy is, and yet we managed to take a sharp picture of this thing, all because we invented a synthetic aperture of a telescope the size of our planet. However, how does that relate to dark matter? No, it does not. However, we have a problem, because I told you something earlier. Interferometry has classically used passive phase cancellation, where we allow the actual information, so to speak, the actual collected waves, to interact with each other to cancel out. That is obviously impossible when you have a telescope, for example, in the South Pole, and you have another one in Spain, and another one in Canada, and one in Hawaii. And so what does one do? Well, obviously, Troy, you just collect the data and use it later. That's a huge problem. Because if you need to perform interferometry on that data, you need to know exactly, and I do mean exactly, when it was collected. So one of the innovations of the Event Horizon network of telescopes was to install a hyper accurate atomic clock at every facility. And all the data that was stored during these observing sessions was accompanied by a hyper accurate, and I mean sub-nanosecond accurate timestamp. These facilities are perfectly synchronized when it comes to time. And all of the data that they collect is time stamped, so that a computer algorithm can study the data, crunch the numbers, use its machine imagination to figure out what it's looking at, to make sense of the data. I want to repeat, this would be impossible without the hyper-accurate atomic clocks and also, literally, artificial intelligence. Questions about that? Why are all 3 images on the results from different puzzle pieces slide look like images of black hole, not like comet or a horse? Looks like bias towards... No, so hold that thought. Let me go back. That was the exact opposite. That's a very good question. Hold on. The point of this, really, the point of this image was to demonstrate that bias was not being inserted into the process because it gave it, for example, images of what they essentially want it to look like. They're giving it images that are vaguely related, and they're giving it wildly incorrect, totally random images. But based on the data, the simulation, or rather the imagination, the machine learning output resembled the target image. This proves that even though we were trying to, let's say, confuse it, so to speak, to disrupt it with junk data, it still managed to create essentially the identical image. That tells us that we are not injecting bias into the picture. Now, if this image looked perfectly like a black hole, if this image looked like one of the nebulas in that picture, and if this image looked like one of the people, like the elephant or the man or the cat, or there's a dancer up there, then we would know that we had, unfortunately, even despite all our best efforts, injected bias into the algorithm. The fact that the data generated the same picture, even when you provide it with this bogus data, demonstrates that the algorithm is essentially doing a lot better job than the human operators at keeping bias out of the process. Does that make sense? Yeah, so Ed says this proves bias to a high degree. So that's a very good question, but I want to make sure we understand that. They were very careful to do the opposite of injecting bias because they were deathly afraid of doing so, which would, by the way, make the whole project worthless. Because, I mean, what would be the purpose? You start out with an expectation like this, based on the math, but it's a simulation. And by the way, what we ended up getting, as you can see from this drawing, and by the way, this is a simulation, what we ended up getting did resemble it. And what we did hopefully confirm with our experiments is that the data is real and not a product of our expectations. What Troy said would be a high bias. Yeah, right. By the way, that's probably the most important philosophical concept in this entire presentation. So let's make sure we understand it, because it would be very easy for a hyper-skeptical person to see this and go, oh, well, this is not real. It's just machine learning and fantasy. This is just literally the dreams of a computer, So, like the Blade Runner thing, what is it? Do androids dream of electric sheep? This is just electric sheep, It's not bad. Next slide. So I think we understand. Let me go back just to make sure we get it. This is the network of data points. This is the expected image. This is the actual data we get, and then we deal with the quote infinite number of possibilities unquote. I'd love to know why my system is not proceeding. Go to the next one. We then take the data, we try to corrupt it on purpose by feeding it junk, and we are delighted to discover that the end result is the same every time. Does that make sense? Yeah, I like that. I like the way Ed put it. We tried our best to confuse the AI, and it still got it right. By the way, it's not so much a matter of right. It demonstrates that it's basing its criteria on the data. And, it's funny, dealing with an AI program is very much like dealing with a living thing, because no matter how good of a computer scientist you are, it's still going to behave in unpredictable ways. And I did see if you do some research on this, you'll find some very funny examples of that, where it does things they didn't expect. One of them, they were training it on shapes that are not expected to be in space, like snowmen, and deliberately creating bias and deliberately keeping out the real data. And they started to get these bizarre, like snowmen-like monster things out of the algorithm. Puzzle pieces training set not available. Oh, very good. Training set, not a validation set. I like that. Okay, that's a good way of putting it. Thank you. I hope that makes sense. I hope that computes. That's funny. Now let's talk about someone who became famous against her own wishes, because she's a very humble person. This is Katie Bauman. And you can see her standing in a room. I showed you this last week. I love this picture. It's one of my favorite pictures, because she's standing in a supercomputer center, and I believe it's in Germany. She's got a bunch of hard drives in front of her, which were mailed in these boxes. Airmail, of course, in some cases because of the South Pole. And the funny thing is, in some way, there's not that much urgency to the mailing process because, well, let's see if, you know what? No. I want you guys to tell me the answer to this question. Let's say one of the airplanes was a week late. Let's say that because of the weather in South Pole and Antarctica. Why doesn't it matter? Let's see if you were paying attention. Why doesn't it matter if one of them came by UPS and was 2 weeks late, and one of them came by FedEx and was 1 week late? Why do we not care? What do you think? Someone answer that question. Why would it not be a big deal if the mail was late, so to speak? Let's see if we get it. This is a timestamp. Very good. Without those timestamps, this entire experiment would be a waste of time because that data would just be a bunch of gobbledygook. It would need to be utterly, utterly perfectly synchronized, or else it would be completely worthless for interferometry. What's extraordinary about this experiment is we're talking about a supercomputer doing something that classically could never be done after the fact. You had to perform, and still do usually, you have to perform interferometry now because you're allowing the data itself, the actual signal itself, to do the cancellation naturally. This is extraordinary because it allows an example of computers doing interferometry after the fact. And what's exciting about this is it might open up the doors for retroactive discoveries using old data. If we can create like virtual timestamps and see if we can how much we can get away with as far as inaccuracy and whatnot. But this is an example of utterly, utterly meticulously timestamped data still being useful even though it was collected weeks or months in the past. Questions about that? So Slavna is asking about that process. Actually, if you read some of the if you look at some of the PowerPoint presentations that were done by some of these grad students and doctorate students, they actually have examples of that where they would use wild, weird pictures. I mentioned the snowman one. They got some pictures that looked like a snowman, but it wasn't quite a snowman. One other example of this that you might be more familiar with, everybody watching, is have you seen those terrifying Google AI images where you give it a picture of like a chair or something and you tell it to process it as a living thing, and it superimposes eyeballs all over the chair, and it has this weird, crazy psychedelic background that has like a river over here and like a building over here and like a burning tree and all. It's like some kind of crazy like impressionist painting made by a machine. And that's an example of AI that is not being well constrained, where it's just saying, okay, go out on the internet and try to figure out what this looks like. And it does. And of course it fails miserably, but it does produce an interesting image. It is kind of fascinating when you consider the fact that those crazy pictures are the imagination of a machine. Yeah. So to Ed's point, yes, they did quite a lot of testing like that. And again, the purpose of it was to make sure that they were ruling out the possibility of an image of a black hole that happened to look like their simulations, because they had accidentally biased the algorithm by feeding it with information of what they thought a black hole should look like. And that, in a way, it's like you're treating the computer like a living thing, and you're giving it its own space and saying, okay, we're not going to over-inform you because we don't want you to inject too many preconceived notions about what this should look like. We want this to be as data-based as possible. Yeah. So we mostly got through the conversation. Are there any questions about this? Something I'll tell you cool about Katie Bauman. She's not an astronomer. She's not an astrophysicist. She is a computer scientist. And I would argue many times, not just because of her example, that this imaging of a black hole is not a triumph for astronomy so much as it is a triumph for computer science. This is an example of one of those discoveries that would be absolutely impossible without computers. You couldn't just point a radio telescope at that object and expect to get an image that looked anything like the black hole picture that we got. I don't get that analogy. Can someone explain that to me? Like a Klein bottle. I don't understand. Someone can explain that to me. So I didn't really end on any big points or notes or climactic conclusions, but are there any final thoughts? I'm going to start wrapping it up. She's quite young, too. When this was done, she's only 29. Remember that? Actually, don't remember that because I don't want you guys to get discouraged. Oh, no, I'm 35 and I haven't discovered the next form of computer thinking. I'm a failure. No, please don't do that to yourself. Some of us achieve great things early and then ride the slide down the hill. Some of us climb up the hill. Some of us have a hill that looks like this. Your career has so many ups and downs. Please don't worry about the fact that some people discover new things in their 20s. It is impressive, though, I will say. The dare to dream crowd, people who are like, I won't be stopped by unlike. And by the way, they were not optimistic. I've seen multiple interviews with multiple people on the team of the Event Horizon Telescope, and the pessimism was hilarious. I mean, these guys are like, yeah, it's not going to work. And there were so many things that they did where they didn't. I love stories like that, by the way, when astronomers or scientists are overly pragmatic about something. They're like, nah, the odds of success are exceedingly a little thin, but at least we tried. And then they succeed, and they're like, oh, what a surprise. We actually knew what we were doing. I can't believe it. I love stories like that. Yeah, so. Oh, yeah. Yeah, Mobius strip in a case. Yeah, in bottle. That's right. I get it. Yeah, I forgot that they were called that. Cool. I don't know how that applies directly to this, because it's not truly an infinite number of possibilities, because there are going to be constraints, and hopefully as many as possible in the form of data, hopefully, and not just conjecture. But in the Mobius strip, you're not really changing it based on, there's really no constraints that I'm aware of. But anyway, wrapping it down, let's look at I'm going to look at my chat again really quick. Let me go back to that exciting picture of excitement. Yes. So you can tell your friends that it's not actually a picture of a black hole, but it is a picture of the accretion disk around one. Hopefully we learned a little bit about interferometry tonight, and also about machine learning. I'm just looking through my material, seeing if I forgot to show you anything. Quiet chat. Is this too much for you guys? Is this topic too mind-bending? Yes. Is this the end? Of course not. This is the beginning. And one of their studies also include Sagittarius A, the black hole at the center of our galaxy. Again, ironically though, I think this is interesting. The images of Sagittarius A will likely not be of as high fidelity as M87, despite the extreme difference in distance, because of all the stuff in the way. It's very hard for us to study the core of our galaxy, even in radio wavelengths, which pass through material, because there's so many other objects also emitting radio waves. In the case of M87, as you saw, it was in a big, relatively empty patch of sky, and that allowed us to look essentially directly at it. And by the way, there will be other black holes as well, and of course we will continue to increase the resolution of things like this, of these systems. I look forward to the day we put a radio telescope on the moon. That'll give us a synthetic aperture of 240,000 miles. That'll be pretty good. And of course, we can keep going with that. All right, let's give you a little brief on the next week's show, just so you know what's going on. Like I said earlier, we're gearing up to reopen our facility. I'm happy to say. I'm very busy. I'm also going to take some vacation, which is outrageous, I know. And then we're going to hopefully start reopening with limited capacity for a time. By appointment only, by the way, so don't just show up, please. I need you guys to not do that, please. And because of that, next week will be our last episode of Goldendale Observations for the next few months anyway, maybe weeks. So it depends on how it goes. And this episode 20, that seems like a nice round number, episode 20. What I said earlier remains true. If you have questions or comments, please bring them. I hope to make that show more of a question and answer show. And we're going to talk about different kinds of space objects. So things like nebulas and supernova remnants. And what else we got? Galaxies and star clusters and globular star clusters and planetary nebulas and a lot of other things. So all these things we're going to talk about and more, and hopefully learn a few things about. So as we wind down, any final thoughts? What other object would you look at using this telescope? That's a good question. I would argue, in this particular, it's a very good question. Any object that's first radiative in radio wavelengths, obviously, and objects that are so extraordinarily compact that you cannot reliably observe them via any other mechanism. So you would use something that emits radio waves, maybe dim, but maybe not. I should add that the gain of the Event Horizon telescope is not very good because of what we talked about earlier, because the telescopes are so far flung, because they went for resolution, not for gain. So I would actually argue not dim objects, but relatively luminous objects. So relatively luminous, radioluminous, highly compact, and or highly distant objects would be essentially the likely targets for the Event Horizon system, and future technologies that employ the same concepts. Of course, it would also be helpful if they were to fill out the network with more telescopes on the inside, so you have less of these slices and more of a complete pie, so to speak. That's a good question. I think it's neat that the rotation of the Earth is used so critically as part of the experiment. That the rotation of the Earth makes it possible, essentially. So you don't just have point sources of data, but actual arcs, so to speak. Yeah, like that. Okay, I'm about to wind it down. Let's see. Well-deserved dedication. I'm glad you think so. Angular view of a size of orange on the moon. It is something, isn't it? And I think pretty darn impressive. So, some final thoughts. This has been a fun little experiment. This Goldendale observations. If we do resume in the future after next week, I would like it if we could involve more human beings. For example, maybe the same format, but with a live studio audience. You know, like an old sitcom. You know, ha ha. And we're not going to do a laugh track, but that'd be hilarious. Yeah. And I appreciate those of you who have come almost every night. Some of you are very reliable fans of the channel. And in general, Washington State Parks, YouTube, and also Facebook, we're putting more and more effort into digital outreach. And so, if you've enjoyed yourself, please like and subscribe. And this was Due South. Is that from that show? That was a good show in the '90s. What about Due South? Oh, we need an observing location on Mount Everest. The problem with that is it's going to be a horrible place for the telescope and also for the technicians. And so, big fan. That's nice. Thanks. I would attend and be quiet too. Yeah, sure. Okay. On the pole. That's fine. Well, this has been a fun topic. I'm glad it didn't go over our heads. I think we get it. And if there are some questions lingering after the show tonight, feel free to bring them with you next Sunday. It'll be your last chance for a little while. All right, my friends. I'm signing off. Be safe, and I'll see you next week.